Hey, this is Warner. We're going to take a look at number 2 for the momentum review. So you have a crossbow, fires a dart at a very high speed, and a student wishes to find out a student wishes to determine here the velocity that the dart exits the crossbow mechanism. So what you'll have to do here is you need to add the word determine the velocity. So they forgot that on this one. Oops. Oh, well, we've added it now, so we're set. So they want to determine the velocity of the dart exits. The student can't simply divide the distance by time because there's no way to do that. There's no equipment there. So you've got a wooden block, some string, a meter stuck protractor, and a scale. And they know that the best way to do this is to hang it from the ceiling, hang the block from the ceiling, and fire that crossbow so that that dart sticks in and the block swings upward. So you've got your crossbow here, and so we'll kind of make the crossbow look like this. And then we've got a string, and it hangs down, and then you've got your block. And what happens is that dart hits the block, and when it does, then this whole thing swings up. So it's very similar to some of the other problems that you've kind of seen us do. Now you have this arrow sticking into it. And from this, we can measure the height or the change in the Y position of that block. And from that, you can figure out what that speed is. So one of the things that we need to have is we need to know the mass of the block. We also need to know the mass of that dart. And we've got to use a balance to do that. So balance, or you could use a scale. So either one, if you mention it, would be fine. And that would be 1 point. The second one is to mention the original and final height here. So this would be the final height. This is the original height. That is the second point. And then you just had to have the diagram. So if you had those three things, so you have to mention finding the final and, oops, you know what? Those are velocities. I want the height final and the height original, sorry. So the final height and the original height. Mention finding those, and then you have to draw this. So the mentioning is one, and then this is another one. Okay? So it says, now explain how the student can use those measurements made in part A to determine the initial speed of the dart. So let's go through those measurements again. So we have the final height, we have the original height, we have the mass of the block, and the mass of the dart. So we have all those things. And what they want us to do is go through, and we can actually make two equations for this. One of them is a conservation of energy equation, and we can say the mass of both the block and the dart times gravity times that change in position. So if I subtract these two, I'm going to get my change in my position in the y direction, and that should be equal to the kinetic energy at the bottom. So that's 1/2 of the mass of the block and the dart times the velocity of the combination squared. The next thing that we can do is that's 1 point, and then the second point for part B is just looking at conservation of momentum, and we can say the mass of the dart times the velocity of the dart should be equal to the mass of both the block plus the mass of the dart, and then their velocity is final, and then we can just, we don't want to square that. That would be bad. So instead, what we're going to do here is we're going to get rid of that square. So we don't want to square it. We just want that final velocity. So remember, we're dealing with momentum here. All right, cool. So that's the second point. The next thing that it says here is the student is not able to vary any aspects of the crossbow, the dart, or the hanging block. How is the student going to be able to get a pretty precise measurement here? And all you have to do is just say it needs to have multiple trials. So you need to do it several times in order to find that, and that's worth 1 point. For letter D, the next thing that they want here is they want E to represent the total mechanical energy of the dart block earth system. And it says, how does the value of E change as the dart becomes embedded in the block? So for this one, we're going to say that the energy decreases, and the energy decreases because the energy consists, so the energy is equal to the kinetic energy plus the potential energy. And in an elastic collision, that kinetic energy changes into other forms. So the kinetic energy will actually, in an inelastic collision, the kinetic energy will go into sound and will also go into heat. So that's why the total energy will decrease. Okay? So the other thing that we need to do here in D part double I is it says, how does the value of the energy change as the dart and the block swing upward to their highest point? So this is as it becomes embedded. It's going to shoot out, and then when it goes in the block, it's going to go thunk. So it makes a sound. So you're going to remember the sound, and then there's also heat there. So this is not, this is going to lose a little bit. So we could actually, if we want to, we could say that there's some ETH there being lost. For part 2, this energy will remain the same because now we have the kinetic energy is being transformed into potential energy due to gravity as that block swings upward. For the next part, which is letter E, it says, let P represent the total vector momentum of the dart block system. Does that momentum change as the dart becomes embedded into the block? So if you just kind of think about this one and you think about what can be and what cannot be conserved, that momentum does not change. So you're going to need to say no here because either the collision is instantaneous and it takes time to change that system's momentum, or there's no external force. So we either need to say that the change is instantaneous, it's instantaneous, but I think the better thing to say here is there is no external force. There's no external force at the instant of collision. For the second part, does the momentum change as the dart and block swing upward to the highest point? So yes, it does change, and it changes either because the system slows, so you can put that, or you can say that the system's motion changes direction, so the system changes direction, and these are all ors, so you can put any of them. System changes direction, or the tension and or the weight exert external forces. So now we have tension or weight, exert a external force on that system. And then for letter F, this one is 2 points, so each of these letters are 2 points. Letter F, it says, suppose that rather than becoming embedded in the block, the dart bounces backward off the block. So they want to know, will the block swing to a higher point, lower point, or the same point? So should be a higher point, because remember here, when the dart bounces off the block, then the dart has a much bigger change in momentum. So when the dart comes in and it hits the block, then it's going to bounce backwards and come the other way. So the dart's going in, and then this dart is going out. So it's kind of falling away. And if it does that, the dart, so here you're going to have to say something about the dart has a change in momentum that is large. And because of that, it should impart a bigger speed. So there should be, therefore, you could put 3 dots and say, therefore there should be a larger speed. Okay, and if there's a larger speed, and then that would transfer into a bigger change in potential energy. And by conservation of energy, that's really what you need to have. So you get 1 point for talking about that momentum change being large. Because it's large, you get a larger speed. And then with a larger speed, you're going to get a bigger change in energy. And that, really, believe it or not, is a 12-point question.